All right. Been a while since I last had a stream. I am just thinking, how do I want to do this? Maybe I'll pull out a new tab. Put this to the side. Let me see. How did we do it? Okay. I'm trying to remember shortcuts on this keyboard. All good. It's working as expected. Now we can do some Leetcode. I'm gonna do a monkey type because I haven't done one in a while, actually. And we're gonna change it to Python 5k with custom quotes. Okay. All right, that's nice. That is nice. It's in the sense that it's pretty fast. I should sign in. Okay. Yeah, it's been a while since I've done consistent monkey type. Definitely. Okay. Now, I had a look already at the solution that I'm about to do. This problem I'm about to do. So I'm going to just start writing this solution out. Maybe I'll explain it first. So from what I remember, watching the Leetcode solution is in this problem. So you are given a 2D grid of integers matrix where each integer is greater than or equal to 0. Return the length of the longest strictly increasing path within matrix. From each cell within the path, you can move either horizontally or vertically. You may not move diagonally. So the idea is to reduce the repeated work when you're doing a DFS on the grid. So when you do the DFS, you would imagine that you would possibly reach a certain grid multiple times. So if that's the case, it is good to store the result of that specific cell within the cell itself. And then so you would have each of these cells consisting of the number of the longest possible the number of the longest strictly increasing path. Yeah, so the length of the longest strictly increasing path would be in one of these cells. So in this case, you would imagine that it would be 4 here, 4 here, 4 here, and 4 here because, well, it makes up. Actually, no, that is not right. You would know that there would be 4 here. This may be 3, this may be 2, this may be 1. I think that's the idea. And then you just take the max of each of the values in the cell. So each of the values, yeah, in the grid. Okay, we have hints, which is nice. Yeah, recommended time complexity. So hint, if we move one cell to an adjacent cell with a greater value, we don't revisit a cell. The path is strictly increasing. Yeah. A brute force approach would be to run DFS for every cell and return the longest path found. This approach is exponential. You can think of a way to optimize it to avoid redundant calculations. Yes, you can, by using a DFS, but by using a memoization. You can use memorization to cache the results of recursive calls and avoid redundant computations. A hash map or a 2D array can be used to store these results. I'm trying to consider if there is a good bottom-up approach to this. Because I can think of the recursive DFS approach. And there's no problems there. But for a bottom-up approach, that'll be slightly different. Let me write the recursive approach. I'll just do it. So we're going to use a DP. We're going to set a 2D DP. Okay, so I gotta consider the rows and columns. And we can always assert that the matrix is one or more. Yeah. So cols or rows? Control F. Yeah, so this should be fine. You need to give a row and a column and some previous value. I know that you're gonna have to use some previous value. A row and a column, so it's gonna be like a dr. So it's gonna be row plus dr and row plus column plus dc, and the previous value being the value at the matrix row and column. So the row and column, and for, let's see, for drdc in directions, where directions, so I'm gonna set directions outside of the solve function because that's just always going to be the case. So we're going to go 1 0 0 1 -1 0 and 0 -1. Okay, so those are all the directions possible, and you do a solve and you do a check that the row is 0 is less than row so row has to be, if row is less than 0 or row is greater than equal to the rows, all possible rows. So, or let's see, C is less than 0 or C is greater than or equal to cols. Return what? You return 0 perhaps. So when you do this calculation, something's got to be considered. Or the matrix row and column so we're going to try and look for strictly increasing. That means if it's less than or equal to the prev value, then you would also return 0. As in it takes no effect. Solve is to return the max. Of something. We need to also consider the dp of row and column. If this does not equal to 0, return dp of row and column. After we do this, we also need to set the dp of row and column equal to the result. We don't return a max, we return the result of something that happens here. Yeah, res of max, current res, and 1 plus. And res could start from 0, I think. I think it doesn't matter what you set res here to be. Does it? Doesn't matter. 1 plus 0 should just be 0. You solve from a given row and column and you start from -1 because you just need to assert. I mean, you can start from 0, right? Let me think. No, it could include 0. Actually, you need it to be -1. So for row in rows, the range of rows. For C in cols, range of cols, we would do this calculation, and then you would return, yeah, so the max, you would take the max. You would need to flatten the array. If you take the max of the inside list, for I in TP, it takes the max of that, max of the final list, and you just get the max overall. Which is fine. I think this should be fine. Jotor, hello. Y, G. We go to the Leetcode problem. Okay, so yeah, this was my attempt. I didn't get right first time around. Let's go. Copy it all. Oops. Okay. Copy this. Paste. Run. Cool. I want to know if there is a bottom-up approach to this. There should be. I need to write. So what's this called? Longest increasing. Okay. Longest increasing path in a matrix. The solution was easier than expected. Simply by noticing you can use a depth first search. DFS and a memoization, a dynamic, from dynamic programming. I'm curious to know whether there is a bottom-up approach, which there should be. We kind of already know the recurrence relation. $329. Okay, let's have a look if there's a approach to this that is bottom up. Topological sort. Okay. For sure we have a top down like this. But we can use topological sort. We can use topological sort, which, fair enough, let's bring up topological sort. let me just search this up also. Can every... Does every top-down dynamic programming problem have a bottom-up approach? Hello, Shah Jalani. There should be. What's good? Nothing much. What about you? Okay, theoretically either way works, fair enough. But how are we in fact thinking about this in terms of topological sorting? You're just meant to implement topological sort on this? So everything, so this is a directed acyclic graph. And because of that, you can create a topological sort. Right, so this is a topological sort, but it's also a DP. So a DP isn't even related here. Is it? No, maybe it still is. Maybe it still is in topological sort, because I remember reading about this not long ago. So we have now we can, for example, calculate the number of shortest paths from node 1 to node 5. Or you can find the shortest path, right? 1, 2, 3. So count the number of paths. Okay, well that's a different problem. My recurrence relation is going to be something different. So yeah, what is the shortest versus longest path? Yeah, this is the problem of dynamic programming using a directed acyclic graph. Doing fine. I've been on meet right now. I'm not sure what that means. So I think I can try this. Yeah, so my problem was definitely related to, so what is this is my problem that I'm trying to figure out, and I got to figure this out using dynamic programming. Yeah. Yeah, I understand. One call, okay. I won't disturb you. Okay. So for wherever there is a top down, there is a bottom up to this. And if I were to just think about how this bottom up approach would occur, this bottom up takes three things as inputs: the row, the column, and the previous value. Or do I just have the row and the column? This is the recurrence relation. Take the max of all four possibilities. Yeah. Like you could, I suppose. So this is probably an example of one where the top down is still easier to do. So the solution we have here is one. So this problem is one example of a dynamic programming problem that is better solved in top down. Mainly because the bottom up approach would have us storing multiple DPs. DP arrays. I believe. So topological sorting, I could see. Yeah, topological sort solution. So then my thinking is how I should write that. Alright, let's try and write this topological sort solution. Should I write it? So what is it I need to build for this topological sort? The actual adjacency list for the graph representation. I could. And then after that, so the adjacency list, yeah, okay, that's fine. But if I build this adjacency list, what I care about is probably just the in degrees. Well, not the in degree, but the in arrows, the edges. The in edges of a specific node. And when we build the topological sorts, what's the plan? Do we need to build a topological sort? Because we built the topological sort into an array. Yes, it would build into an array. But then what? When you build it into an array, you just have the numbers in that order, right? There's nothing else. So in order to find a certain value, you need to keep a DP. And go through the topological sorts, perhaps. So let me have a look here at the Computer Programs Handbook here to help us. If a directed graph is acyclic, dp can be applied to it. So this is just a straight fact. So any DAGs, you can apply dp, apparently. I'm gonna write this down. Page number 161. Double check by clicking it. $151. Yes, okay, that is the page. Hashtag DAG. Directed acyclic graph. Wait. Okay. So I want to say that alright, let's look at this example of counting the number of paths. So an example, let us calculate the number of paths from node 1 to node 6 in the following graph. There are a total of 3 such paths. So we know 1, 2, 3, 6, 1, 4, 5, 2, 3, 6, and 1, 4, 5, 3, 6. So let paths denote the number of paths from node 1 to node x. Alright, so in our case, okay, so let longest increasing path let's solve x denote the number of the length of the longest increasing path. The length of the longest path is fine. Increasing path is fine as well, I guess. As base case, paths 1 is equal to 1. So the length, okay, so from node something to something. Oh, yeah, okay. Maybe in a topological sort, can you start always from the left side? Is that true? Yes. Maybe. Can there be multiple topological sorts? I'm going to look at the example here that we were given. If we're given this equation or this example, you could go you go from here to here, or from here to here, to here to here, or here. And this one, yeah, is connected to this 3. 5 points down to these, and 5 points down to 2. So from a topological sort perspective, there could be a start node at any one of these, 5, 5, or 6. So does that matter? Let me just have a look at topological sort again. Yeah, so it's not necessary that the first node here So if we didn't have this 4, then you have a 5 and a 1. And the 1 could come before the 5 or the 1. The 5 could come before the 1 or after the 1. Okay. Yeah, okay. I think I understand. That means you can start from left to right on the topological sort. Yeah. And when you search through the topological sort, that number points to some number. You just know that. And then you can keep on searching. Yeah. Not the best approach. Or is this where the bottom up comes in, where you do the opposite way? Okay, so if you have this, the path X with the sum of all the paths before it. So in our case, it's the max of all the paths before it. It's the max of all the paths before it. Clat. Hello, man. By the way, should you practice behavioral as much as technical? I would say no, generally. But you should have enough hours practicing behavioral and enough hours practicing technical. It's just that I feel like you'd spend more hours practicing technical than a behavioral, that is. You need to build confidence talking about your projects. I see. And yeah, you might need to sit with someone and talk about that. Like creating stories and making it seem like I did a lot. Is it possible that the stories are not detailed enough? That's what I'm thinking. Because if you feel like it seems like okay. Right. I mean, I think I can also suck at explaining sometimes. But yeah, it comes down to practice, right? And just take the time. Take the time to practice speaking. And if you're writing stories, remember to just write them in dot points and just like kind of succinct dot points, so that instead of relying on reading the notes directly, kind of understand the dot point already in your head and just speak from there. I know it's probably harder to practice. Like it's harder to actually do than it is to say to do. Okay. So the recurrence relation is what? From node, so from a start node from a start node to an end node. Okay. So the recurrence relation is solve x is equal to the max of solve of the previous path. Alright, so we're going to call it A underscore 1. Now this is 1 plus solve. So instead of doing it like this, is there a better way to express this? Yeah, it's alright. 1 plus solve A2 dot 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 1 plus solve A underscore 3 or N, let's say. Okay, I think that's what they use. I could represent it like that, or I represent it some other way. Yeah, I think that's fine. That's fine as is. So with that in mind, I should be able to continue. With that in mind, from a bottom-up perspective, how do we think? I'm going to say where A1, A2, AN are all in degrees, in degree nodes. Okay. If they're all in degree nodes, then it means I can process it from the largest number to the smallest number, which I think makes sense. Okay, let's see. I think I know how to solve this now. I'll just have to write it out. I'll rewrite it here. Actually, I might write it here. Restart the code editor. Would I need in degrees only? Trying to think. Do I need in degrees only? It is directed. What do I need? Do I need to build both? Let me check this again. From start node to the end node. A start node. An end node. Start node. And an end node. Doesn't matter. It will give us a list as an output of the topological sort. Use each of the elements in that list, in that topological sort, as the key to our adjacency list. To know what to search for next. Right. Yes. So we build out this DP array. This is kind of a top-down. From the bottom up, what we need is the in degree. So this itself, this topological sorting only needs an in degree list. And then for the bottom up, you can go from, the topological sort to list and come back like bottom up. So if we start from, in this case, 6, then 6 itself, we know that's the base case of 1. we know that the longest length for that is just 1. And then for the next in degree, check the adjacency list of the in degree. No. Yeah, know where it comes from. But that doesn't help, does it? In any case, if you go from left or right, it doesn't matter, I think. Okay. All right. So I think all we need is an in degree anyway. Yeah, all we need is an in degree, and then we just reverse the output topological list, topological sort. We'll just keep the topological sort from the very top to the bottom. Is there something called a bottom logical sort? You need a topological sort, and then go from the leftmost element in the topological sort and see if there's any integers for that. If there's none, which it is the case for base case, then you can say that's 1. And you go to the next value, and that next value, if there's any integers for that, then you would consider those two parts. Yeah, okay, perfect. I think I got it. I got to do it now. In degree. I will want to see though, because they do say in the solution they use an in degree, right? And that's the only thing they use, I think. Alright, so if that's the case, then let's why is that an in degree 2D DP? I was going to use an adjacency list. Maybe let me call this just an adjacency list of the in degree. Let me also double check in degree meaning. So it's the number of edges coming into a vertex of a directed graph. So maybe that's not the right term, but in an adjacency list, in versus edge list out. Okay, how to store a directed acyclic graph in an adjacency list. To store a DAG using an adjacency list, you can represent each vertex as a list of outgoing neighbors. I can do it as outgoing neighbors, but I need ingoing neighbors. I mean, it really is a matter of how you define it. It's something to think about, but I think like it's just easier representation. Yeah, I think it's just an easier representation. So I think I'll just go with that. So an adjacency list, an in-degree adjacency list is a list like this. Let's see. We need to check all four sides, don't we? Check all four sides and then add whatever that is to the list. For row in, so we need like rows, linear matrix, cols, linear matrix 0 for row in rows. So let's say range of rows. For column in range of cols, the thing becomes so matrix of row column. Building this graph is going to be interesting in itself, because considering all sides, so we need the directions, which is a list, which is a tuple of the possible directions. So -1 and 0, 0 and 1, 0 and -1. Of these four directions, so the dir, so for dr dc in directions, so if this value is strictly is less than or is greater than, I think it doesn't matter. It doesn't matter. Does it? It might. Maybe. Maybe it doesn't. So I'm trying to think of how to most intuitively think about this. Yeah, you can think of it as the next. So R plus DC is like the next one. So you would expect that to be the greater one. And if it is the greater one, then the adjacency list. So we're pointing smaller values to larger values, right? So In this case then, the adjacency list of, I could put the row in the column. Or do I put the number itself? Not the number itself, because it could be the same numbers. So it has to be the row in the column. So in this adjacency list, we need to use the row in the column as our kind of like index, or as our identifier. And that is equal to the matrix. Okay, that is equal to, that is, we append the value of r plus dr and c plus dc. And this is in degrees. So I should be doing the opposite. Right, let me think. So the drdc is greater than the r and the c. And we want the in degrees. And we are going from increasing. We're going increasing. So this is the right representation. All right, so that's now done with the adjacency list. Now we need to do a topological sort. So how to do the topological sort? So we're going to call it top, or like a sorted top sort. Of all of the adjacency list. So if you have, how you go about this, right? Is you can start from any value, right? From any value to topological sort this. Is there also an inbuilt Python thing? Topo sort. I mean, topological sort here is probably useful somehow. Meh, I'll just implement it anyway. Good graph practice. So topological sorting algorithm is, the idea is to go through the nodes of the graph and always begin a DFS search at the current node if it has not been processed yet. During the searches, the nodes have 3 possible states. Okay. Initially, the state of each, when you search through a node for the first time, it becomes 1. Finally, after the successes of the node have been processed, its state becomes 2. If the graph contains a cycle, we'll find this out during the search. If the graph does not contain a cycle, we can construct a topological sort by adding each node to a list when the state of the node becomes 2. The list in reverse order is a topological sort. Okay, it doesn't matter where we start, I think. How do we know that it has been added to the list? Keep a set? Maybe. Could be a way to do this. Okay, but doesn't matter where we start, I think. So topological sort is a list. And at the end of it, we need to do a top sort dot reverse. Let me just print that. Right, so in this case you might have if row is less than 0 or row is greater than len, let's say rows, or column is less than 0 or column is greater than cols, you would continue. Okay, and then list index is out of range here. Right. Yes. Because you are only considering when you should be considering. Okay, you should just be considering the next value. We'll have index out of range. We're adding R and C should be fine. Oh, if it's greater than or equal to. Okay, greater than or equal to. Not that it'll ever be greater than or equal to. I think that's right. Yep, and so if I did like 1, 2, 1, 3, we would expect it to be 3, 1 in the printed output. Yep, okay, perfect. Okay, then we can go about our lives further and say, so after you do the topological sort, this is where you do the DP construct. The bottom up DP, I'll just say and doesn't need to be specified that it's bottom up dynamic programming. Probably it's okay without. But we initialize this dp to the 0 times rows times cols. Okay. And by the end of this, what we should return so throughout the topological sort, do we just return the last value, where the last value is equal to rows times cols minus 1. Indexing wise, does this work? Probably, it probably does. I know I can just do minus 1 to get the last value of the dp. Right, but I want to be certain about this. Okay, but the dp performs as follows. We start with each of the values for node in top sort. If node, so the in degrees of the node for so edge list of the node, and this is top sort, assuming you have a row and a column as your key. So for next node in this, next node, the dp of the next node is equal to the dp of so prev node actually is a more adequate term. Just a prev. So prev. Okay, so dp of the node is equal to prev one plus max of whatever the previous values are. Okay, so maybe it's better to write it as 1 plus and dp of node so whichever just is the max at this current point. Okay. And you just remove that and you just find the last one. Okay, so now we can just try the topological sort algorithm here. Okay, so, I've got to implement it at least once, right? So let me try that. How should I do this? How should I do this top sort? Doesn't matter where you start from, right? So for node in edge list, that's not right. So it doesn't matter where you start from. But you need to keep track of what you've already seen during the topological sorting. Right, so let me look back here. Each of these values are assigned a value of 0, 1, and 2. So you need another dictionary. Initializing values to 0. And then values to 1 and 2, if they have been seen. Okay. So seen is going to be some dictionary of integers for a node in right. For row in rows. So rows. So this is len of row. So range of rows. We'll see in range of columns. Seen row column. I know I don't need to specify this, but it's clear to me. Seen row column is equal to 1. So if we do a DFS here. Let me think. If seen row column is equal to 2, so it means it's already done, so we can continue. If it's equal to 1, then it's still in progress. So actually it doesn't, it shouldn't ever be that. We shouldn't ever need to check it here, that is. But we would set it to 1. And we would go so the adjacency list of the row and the column, and then seen of the row and the column becomes 2 after you've done all of the next nodes here. Okay, this is in degree though. In a topological sort, this is all you need, right? Maybe not. When a search reaches a node for the first time, its state becomes 1. Finally, after all successes of the node have been processed, its state becomes 2. Successes. We can construct a topological sort by adding each node to a list when the state of the node becomes 2. Is a top sort. Okay, so when it becomes 2, then this is when we add to the list. Do you need an in degree? You need an out degree list. So there should be a way to make this cleaner. Leetcode topological sort. Adjacency matrix. Now, so given an adjacency list, if I sign in here, will this allow me to see the solution? Just sign up with a username. Should move this to another screen. Okay. Hopefully we can just fill in the password. Pass. No more. Let me stand. Why can I not sign in? Why does the sign up take forever? Oh, we'll try it. Bridges. Okay. Cool, I'm logged in, I think. I'll be able to sign in now. Let's see if this allows me to see the solution. My graduation year, 2028. Okay. What is this? Python. I can put my code here. This is the driver code. Editorial. Yes. Okay. They have solutions here for this. Good. Kahn's algorithm. Okay. Oh, Kahn's algorithm. Okay, that's interesting. Right. So you can use Kahn's algorithm for topological sorting. So that's interesting. I'll need to read through these. Like a rabbit hole, but they're useful. Okay. Given a directed acyclic graph with vertices, find topological sort of the graph. Topological sorting for acyclic is a linear ordering of vertices such that every directed edge UV comes before the ordering. Yep, so we know the topological sorting meaning. The first vertex in topological sort is always a vertex with an in-degree of 0. Topological sort for a graph is not possible if the graph is not a directed acyclic graph. Expected approach, if we will print nodes in descending order of their finishing time of DFS, that will be a topo sort. We'll print the node V only after it goes through all its descendants. This ensures that anything that follows V will have been added to the output vector before V. Yep, fair enough, that makes sense. So you create a stack to store the nodes. Initialize the visited array of size n to keep the record of visited nodes. Run a loop from 0 to n. If the node is not marked true in the visited array, call the recursive function for top sort and perform the following steps. Mark the current node as true in the visited array. Run a loop on all the nodes which have a directed edge to the current node. Push the current node in the stack. Now pop all elements from the stack and push into a result array and return the result. I think I understand it. Now, why is this not fully shown? I see. Yeah, right. You just put everything to the stack. Right. Yeah, you can have a stack. Yeah, a stack makes sense for this. Alright, so that makes sense. Like, that's the whole algorithm that was explained within the Computer Programmer's Handbook. But now talking about Kahn's algorithm. So the main idea is to deal with in-degrees as we know in topological sort vertex. With less in-degrees comes first, which means in-degrees with 0 is the first element in topological sort. So we can apply the below idea to get topo sort. We'll print the node which has in-degree 0. We have no dependency first. Then remove their adjacent edge and update the in-degree of adjacent nodes which are connected with previous nodes with in-degree 0. Repeat steps 1 to 2 until we have a node with in-degree 0. Why there always be a node with in-degree 0 as we work with directed acyclic graphs. There must always be a starting point of a graph that have in degree 0. Yes. Yes. So you calculate the in degrees. Yeah. Still going a little too fast here, this graphic. Why do we queue 4 and 5? Alright, yeah. Because it already has 0. Right, and then queue for 5, 4. Take out 5, take out 4. Alright. See how the queue works. I'll need to implement this Khan's algorithm. So you just need an in degree array, some stack, and you're good. You don't need an adjacency list, but you would later. So it's kind of okay. Yeah, you still need this adjacency list. Yep. It's fine as is. We'll need to change the way we do topological sorting here. Okay. In Kahn's algorithm. Okay. Topological sort using Kahn's algorithm. Via Kahn's algorithm. Kahn's algorithm, we need an in degree list, which is equal to 0 times row times calls, rows times calls, if I'm not mistaken. So it's nice that what I could do is for edge list, right? Let me think. Yeah, okay, so it's better to express this as maybe just a hash table. So default dict int val in edge list. So this is a node.
Yeah, there is a solution.
Adjacency list in degree node is equal to edge list node of len. Okay. And iterate through the first time. If it's equal to 0, yeah, something about this is like for row in rows, then you add it to some queue. Import DQ. So you DQ from a given list. If it's equal to 0, then it's q.append that value. Okay. And then if so while q is not empty, then in degree, so actually we pop from the queue the row in the column. I should just call this a node. So q.pop. So in degree node is gonna be equal to we're gonna find all the ones surrounding it. So if we remove that, then the successes we gotta still consider of this. Okay. Okay. Reversed adjacency list. I need a reversed adjacency list. So technically this is the next node. Next is, so for this node, yeah. So okay, we do use the adjacency list. Yeah. So, and this was the next node, then the next value is the next and the node. Is that right? Maybe. In any case, we need to find the next value. So maybe like it's just a matter of putting it here. Okay. So you don't even use the adjacency list, you just build it out from the matrix. It's not the best way to do things, but you know, what else can you do? Alright, so this is a row and column we need. If this is less than, this is less than the next. Strictly less than the next. Then R plus dr, C plus dc, matrix, should say the in degree of this gets decremented by 1, provided, this is I don't like mixing this here. This is bound to happen anyway. Okay, it's okay. And less than equal to, or minus 1. If in degree of this C plus dc is equal to 0, then Q dot append this R plus dr, C plus dc. And this is only happening for dr, dc in directions. Right, so directions already exists, yes. And again, if r is less than 0 or r is greater than equal to rows, or c is less than 0 or c is greater than equal to cols, you would continue, because that just doesn't exist. And if this was the case, you would do this calculation and append. Okay, and then if it is equal to 0, right? Okay, so when you pop this, this value now is in is now a consideration in the topological sort. So topologically sorted node, right? The top sorts dot append the row in the column. Okay, and then from the top sorts, we can do this. So from, I see. Yeah, so from collections, import DQ. Q.append, right, I just didn't even append anything. Append the row in the column. Index out of range. Right, so again, I missed the fact that we are talking about DRs and DCs. Right. Yeah, in this DP, we can't have it like this, can we? It's not increasing. Unless you say that it's just a formula. The row value times the column value. Can you flatten that? Can you serialize this? Can you translate this? Because in a bottom-up DP, it could just be a node, couldn't it? Then how do you know you're on the last one? What is the what do you check? DP of node. DP is 0. If DP is a dictionary, start from 0. Technically, it should be starting from 1. The default should be 1. Okay, if the default is 1. Did I write this down? If the default is 1. You take the max of the DP values. Again. Oh. Values. Max arg is an empty sequence. Yeah, values of what? Okay. It's almost right. So, test cases. The one where we just have one fails. So I don't want to really make it like this. I want to be able to return the DP of -1, which is the last value in the DP. And some given node, I have 1 and 0 and 0 and 1. Still just 1. So you can't do the sum. What you could do is instead row times column plus column. Right, row times column plus column. If you have a 0 times rows times cols, and then rows, so node, yeah, let's just say node, but node is also equal to row and column. Sorry. Row and column is also equal to node. Then row and column in the DP is actually row times column plus column. If you have 0 and 0, then it's 0 plus 0 is 0. 0 and 1 is 0 plus 1. 1 and 0 is wait, that's all right. 1 and 0 should be column plus 1. Column plus 1, it should be like column plus 1. Man, I don't know how to serialize this. I don't know how to serialize this into the DP. I don't know how to serialize this into the DP. But I would like to, so that we can just go DP and not -1. But is that right? That itself might not be right. DP of -1. Because you're saying what is the value of the row in the column of that very last value. Whereas what I want is for any of the nodes, what is the max value, right? So even in the solution, I'm guessing. Okay, who knows? This is a little different to what I was expecting. Okay, then my understanding here is then that I need to use this. So if values is 0, right? So if DP, then else, wait, if DP, okay. So this if DP, else, the answer should be 1. God damn it. It's gonna fail. Okay, we got accepted. But the runtime beats only 5% of people. And the memory beats... This is a lot worse. A lot worse of a solution. In terms of the general consensus. I wonder where the memory and runtime is going actually. Could be because there's so many like default dictionaries. If I set this to 0, I think I know what happens, right? Like this should just fail. Yeah. So it has to be a 1. Yeah. Okay, well this is a bigger solution to a nice problem. I'm gonna put some links here. What? Topological sort, Kahn's algorithm. Okay, so we use Kahn's algorithm. Okay. This is a great document, full of information. It's not even a bottom-up, is it? Is it a bottom-up? Yeah, it is a bottom-up. Right, because there is a topological sort involved there. Let me see. This again, so for node in top sort, and then implement a this is I'd call this a bottom-up dynamic programming. We use an adjacency list with an in adjacency list. I don't know a better word for that for now. And to implement a bottom-up dynamic programming approach. Yeah, so this is a lot of key terms, very nice key terms. Hello Slayer. And I think I can copy and paste this whole solution. Just cause. Copy this whole solution here. That is ugly. Yep, that is incredibly ugly. Better off copying it here. Right, wait, can I copy it here? Wait, what? I can't control C this? Surely. Okay. It copies it in a wild fashion. Alright. My submission. What is the name of the book? Ah, yeah. So this is a Competitive Programmer's Handbook. It's free online. Just search it up. Alright. Well, the bottom-up dynamic programming here is a lot less code than the whole topological sort code, and then a whole lot less code for the adjacency list creation. Was there even a point to creating the adjacency list? If I could find this in degree without using the adjacency list? Well, it looks like I'll still use it anyway in the bottom-up dynamic programming. Alright, regardless, that's the solution. I will now just finish up and soon call it a day. Ooh, why is this kind of bad? I was wondering, how do you approach a problem you try out the first solution that comes to your mind, even if it's a brute force one? No, usually no. I don't like. Well, sure, maybe I do think about that as the first approach, right? A brute force, but I don't write it out because I know it's probably going to be the wrong solution. So I don't go down a rabbit hole if I can stop myself from going down it. And what I would instead think about is if I still can't figure out the problem for like 5 minutes, 5 to 10 minutes, then I will look at the solution and see the approach and try to learn from that approach, just like what I'm doing now, basically for the last 1.5 hours. Basically, this approach that I'm learning right now is the hard way as it was intended. Because actually for this specific solution, you could do it in a somewhat easier way and a harder way, which is to learn more concepts like topological sort, like Kahn's algorithm. Whereas you might be able to circumvent actually learning all of that if you did it a different method. Hope that makes sense. So we'll think of a solution that can satisfy the recommended complexities. Yeah, so I do try to think of a solution that satisfies the recommended complexities. And if I can't, then I would look at the solutions as opposed to doing the brute force approach. Hope that makes sense. Now, why the heck is something happening here? Side functions, brute services. Changed so that it doesn't perform console IO after the instant prompt. Console output during ZSH initialization detected. Sure, yeah, that makes sense. So then why am I getting this? Because that actually doesn't make sense to me. So this is, let me just have a look here. This is unrelated to any Leetcode practice right now. Okay, interesting. Just do this. I'm very new to Leetcode and I can't get my brain to figure out any other solution than brute force one. Yeah, that's alright. Like, you actually can't, you're not meant to know. That's one thing I think everyone has a misconception on. Like, you're not meant to know the solution before you've done the solution. And maybe you've learnt a few algorithms and data structures. Even knowing those beforehand, at least for me, doesn't help in solving the problem. What helps is doing Leetcode problems and looking at their solutions, and then doing other Leetcode problems that are similar to that problem. And when you do those other similar problems, you have a higher chance of actually solving those from the learning that you had from previous Leetcode problems similar to that one. I know that's a roundabout way of just saying practice. But you gotta practice and look at the solutions. And if you can't figure it out, if you can't figure out the solution to an existing Leetcode problem, look at the solutions. It's just like study. You just have to study something, right? Sometimes you just have to look at the solutions. If you're learning a new concept, you have to, I don't know, like try some problem sets, but look at, an example that was in the lectures or whatever. An example in the lectures is kind of like a Leetcode problem that you're doing at any point in time. Yeah, I don't know. So it's kind of recursive. And yeah, you're doing fine. So just one thing I would say is just don't spend too much time on trying to think about a problem, but try and just like try to just if you get stuck, look at the solution. I don't know what else to say. Yeah. But yeah, anyway. Okay, we freed 8.5 GB. All right, let me exit and go back to Ghosty. Leetcode, Vim. Okay. I will need to consider. Okay, let me just close some of these. Oops. Hold on. Quit. Don't save. Okay. X. Okay, that's not what I want. X. Okay. Shift X or space X? Yeah, space X. Okay. The longest increasing path. So this is the first solution that I had. DG. Okay, we're just gonna paste. Okay, undo. We're gonna paste it from paste it from here. Copy and paste. Okay. Right, quit. Now git diff, we just have a look at the diff here, see if there's anything cool. Yep. So yeah. This is just about like what I expected to be the difference. So git add, git commit. Solved using topological sort. Git push. So how long have you been doing Leetcode? Basically since this this time last year, but on and off. Right, so I can show you my Leetcode history. Let me show you here. Kind of get an idea. So it's been on and off, right? Some months I've kept it pretty consistent, most days, but sometimes, you know, I've had off days where I just didn't do it. You know, this became like every second day at one point. This was like once every week, basically. And then it's just like scattered. And then maybe this first time I spent quite a few days just because what happened here was there was an interview coming up for me. So I did like a full week of Leetcode problems. But yeah, like this is what it looks like. See, 2024, 2023, and only other time that I did it was in November. Yeah. That's it. Rank 1000, I mean 1 mil. Let's in the top 1 mil of Leetcoders. Let's go. Nice. It's nice to know for me. Okay. Yeah, I'm done. That was a good learning of that specific Leetcode problem. So, and that's quite a long, I guess, long note taking. Alright, so I can close this now. And I'll worry about it some other time. Tomorrow maybe. And we can count this off the list. And I won't take a nap. So how do I do this? Okay, there we go. Okay, and we could watch a few lectures now, which might be what I do. Okay. Yeah, I could watch one right now. Yeah, but it's almost the 2-hour mark. I could give it a rest. But I think I'll stick, yeah, alright, fine. I'll do a lecture right now. But we're gonna make it so that you guys can't hear what's being said, unfortunately. And I'm gonna have to add a text to say that I'm just doing a lecture. Okay, where is it? Can't see it. All right. Oops. Probably lock everything. Okay. I think that's fine. I'll put it like plastered over my head. Alright. Alright, and then I'm just gonna go silent now. Just gonna do some lectures. Have a good day too, Slayer. I'm gonna put on, let's see, some headphones to watch this. Program language
models.
That's gonna be a problem. Mainly because Did I not watch the lecture here?
here?
Ngram
Ngram
language
language
model.
models.
I did
I
not.
did not watch it. Yeah.
Ngram language models. Not this
Not this
page.
page.
Not this
Not this
page.
page.
Not this
Not this
page.
page. So
Three.
3.
Mm-hmm. Right.
Right.
So
So gotta save this.
Slides.
Slides.
Ngram
Ngram
language
language
models.
models. Ngram.
I think
I
I
think I
know
know what I
want
want to do
now.
now. Ngram language models.
Okay. Recognize speech. Recognize. Recognize speech. Recognize speech.
Mm.
Damn, hold on.
Hold on.
Let me see.
See,
Mic and
mic and
audio.
audio.
Gotcha. Yeah, it's doubling up. It was doubling up. It was because I put in these headphones. I see. Thank you, JC. It's just funny. Okay. Thanks for noticing. I wish there were a better streaming system for YouTube. How so? You search one thing, click to filter by life. We get is replays and music. Is it? I'm thinking like I want to do the rest of this right now. A conundrum. Do I want to stick to it or not? Most likely not. I'm not explaining fully right now, but how am I off at the moment? This camera can catch noise. Okay. Just playing around with it. What's it called? It's called like Center Stage. Apple's Center Stage. It's actually pretty good. I won't lie. Is it warming up my phone? No, my phone's alright. I'm just thinking I might call it a day. Realistically. Not because I'm tired. Because I've got some thoughts. I've got some thoughts to mull over. Yeah, so I might just call it. But thank you for joining. And for staying. I did some good DP today, so I'm happy with that. And I'm not going to finish this lecture as of now, but maybe later. Probably should just think over some other stuff, so I'll catch you guys later. Peace.